Okay, so because the integral would give us this red area here, we want this black area here. So we could do a typical slice, and then the area of that typical slice would be? Yeah, so area would be length times width. The length would be y2 minus y1, right? Be the y value here minus the y value here times delta x. So that's what we want to integrate. We want to integrate y2 minus y1 dx, but we have parametric equations, so we got to change this whole thing into t. We want the whole thing into t. So what is y2? What is y2?
57.
That's just this y coordinate up here, so it's 57ths. And what's y1? Well, that's the y coordinate of the curve, y1, right? Which would be t plus 1 over t. So there's our y2 minus 1, the height, times dx. Well, dx is going to be the derivative of this, dt. So it'd be 1 plus 1 over t squared dt. Okay, questions on setting that up? We gotta get the bounds next for t. But that's the general idea. You're gonna do y2 minus y1 times delta x, or dx, which would be the derivative of this, dt. Okay, then to get these bounds, we got to say, what do we know about those points? What do we know about those points in order to get the t values? So we're saying t equals what here? Say t1. And t2 equals what? So what do we know about those points? Well, we know y is 57ths. So to get the t values, we want the y value to be 57ths. So it's going to be 57ths equals t plus 1 over t, which is going to give us two values, t1 and t2. So if you work this out, you'll get a quadratic. And if you multiply 3 by t, you get a quadratic. And you're going to get your two values, t1 and t2. And one of those t1s will give you a negative x, and one of those t's will give you a positive x. The t that gives you a negative value of x will be your t1. You see that? And then the t that gives you a positive value of x will be your t2. And then you'll solve that. So we're not going to finish because we're first time's sake. Questions on this one? Anybody? Last chance? Does it make sense? Last chance. Okay, what else here? So let's do a polar example. These head lower, 11 and 12. Okay, for this one, so we know that if we're changing from r's and thetas into x and y's, what do we want to get? We want to get r cosine thetas and r sine thetas, because r cosine theta is x, and r sine theta is y. Okay, so what can we do very easily now to get r sine thetas and r cosine thetas? We want to multiply both sides by r, right? Because I'll get r sine theta, r cosine theta. So we have we'll get r squared equals 3r sine theta plus 3r cosine theta. And what is r squared? X squared plus y squared, right? And so this is 3y plus 3x. So now we need to get in the form of a circle. So that means we need to move everything over to the left and complete the square. We're going to have to complete the square. So we're going to have x squared minus 3x and y squared minus 3y. So to complete the square, you take half of the coefficient of x and square it. So half of -3 halves squared, 9/4. And same thing again, another 9/4. But if so you're going to add 9/4 and add another 9/4, then what we're really adding is what? 18/4 over here. So if we add 9/4 and 9/4 on the left, we got to add the same thing on the right. So there's our perfect square. It's going to be x minus 3 halves squared and y minus 3 halves squared. And that's going to equal 18/4, which is square root of 18, it's just 18/4. And so there we got it. So the a is going to be 3 halves, y is 3 halves, and r is going to be the square root of that. Questions on that one? Last chance. Okay, so what was that? That was this one. Last one. We'll do this last one. Circle has center C and origin radius 5. Okay, another circle, that's circle C. K, diameter with one end at the origin, the other end at the point 0, 13. Red. That's circle K. Circle K. There you go. Strange things are afoot. Okay, so let P be the intersection in the first quadrant. So there's this point here. And we want to find r and theta for that point. So what we need is we need these two circles as r, so say r is a function of theta. And then the red one, circle K, r as some other function of theta. So we want to use our polar coordinates, our polar functions, to get r as a function of theta for each of those two circles. And what will be true about point P? At point P, the r value of this circle will be the same as the r value of this circle, the distance from the origin, right? Okay, so this first one, r is a function of theta. Well, what? So we're always, every point is what? 5 away from the origin. So what equation is that?
Squared plus y squared equals
No, you can go for the r equals 5. Every point is 5 away from the origin, right? No matter what theta is. Theta equals 0, pi over 4, 2 pi over 3. For every theta, you're 5 units away from the origin. So that's the equation. So it doesn't matter what theta is. This is a constant function, right? Constant function in polar coordinates. No matter what theta is, you're a constant distance away from the pole. R equals 5. So here, in this context, r doesn't mean the radius of a circle. It means distance from the pole. Okay? So now, for that circle C, those happen to be the same thing. Center of the radius and the distance from the pole, because your center is the pole. Okay, but r means distance from the pole. So now for this one, we could write the equation for k, which would be what, x squared plus y minus 13. No, it'd be what, 6.5? So you're going to do, the center is going to be 0, 6.5 equals 6.5 squared. Did I write that equation right? So the last problem I did, they gave us an equation with r and theta, and we had to get it into this form. Now this is the opposite. Here we have the equation in Cartesian coordinates, so we want to get it in r and theta. So again, we're looking for, we want r cosine theta. Sorry. We know that x's will be r cosine theta, and y's are going to be r sine theta, and then x squared plus y squared is going to be r squared. So we're going to use those to turn this thing into an equation of r's and thetas. So this is x squared plus y squared minus 13y plus 6.5 squared equals 6.5 squared. So multiply it out. These go away. So you have 0. And then what's x squared plus y squared?
R squared.
R squared. What's minus 13y? Minus 13 r sine theta equals 0. So therefore, we've got r squared equals 13 sine theta, 13 r sine theta. R equals 13 sine theta. And there it is. That's r as a function of theta. There's our g of theta. So given an angle theta, this tells you how far away from the origin you are. So when r is 0, you're 0 away. Or sorry, when theta is 0. When theta is pi over 2, you're 13 away from the pole. So we've got this function for circle K, and we've got this function for circle C. And we want to know for point P, we want to know the point such that the radius on circle C is, or the distance from the pole is the same to both circles, right? Because this is the only angle for which you have the same distance away from the pole. So therefore, we're going to set r's equal to each other. We want r to be the same. So we get 5 equals 13 sine theta. So theta equals arc sine 5/13. And what is r? How far are you away?
5.
5. Because it's on the circle C. So that's that point right there. 5 comma arc sine 5/13 is point P.
What's the symbol for a circle?
Say again?
What's the symbol for a circle?
I don't know. What do you mean?
Like, you can draw a triangle or like an angle. Is there a symbol for a circle?
So when you draw a triangle, that's the symbol for a triangle?
No. Like, I want to name it like triangle ABC, for example.
Okay.
So I put a triangle, and then I say ABC.
I've never seen, it's just a capital letter.
Okay.
Because it'd be too confusing with an O. Okay. So we're going to press on here. So we were working on an example last time. Oh, so we have the other thing. Let's see. Let's go on. So the other part of the homework was that sheet. Let's do some of that. So in terms of graphing, I'm not going to take the time. This is kind of review from pre-cal. You need to know how to sketch these. You need to know how to sketch these. So now here, given that graph, so here now, given that graph, can we sketch what's happening in the polar plane? So which one of these three should I do? 4, 5, or 6? Request? 5. 5? So let's look at number 5. So we're gonna think about turning turning the angle counterclockwise, and as we do that, looking at what r does. So when we turn the first quarter circle from 0 to pi over 2, r goes from what to what? 1 to 3. 1 to 3. So when r equals 0, when theta equals 0, we're at r equals 1. And what's going to happen? So r is going to increase to 3 by the time the angle gets to pi over 2. So at pi over 2 is going to be 3. And it's going to increase. So we think about, you can kind of think about looking at each of these radial lines. You're going to be farther down each radial line than the one you were before, because r is increasing to 3. So maybe something like this. Okay, and then what? When you go from pi over 2 to pi, we go back to 1. So it's going to kind of undo what it did, right? So we went from 1 to 3 as we did the first quadrant, and then the second quadrant, we're going to go back kind of in a symmetric way back to 1. Here's 1 at pi, so it's going to do this. And now as we go in the third quadrant from pi to 3 pi over 2, this is kind of an easy one. So as we go from pi to 3 pi over 2, r goes from what to what? 1 to 3. So here's positive 3 at 3 pi over 2, and we're going to go out like this. And then in the fourth quadrant, we're going to, at 3 pi over 2, back to 2 pi, r is going to go from 3 to 1. So it's this peanut shape. What is the equation of this graph? Center line is at 2. We've got a full cycle at pi. So if the center line's at 2, that means we're going to be adding 2. So r equals, and then this is we can model it with either, but is this more easily modeled with cosine or sine? No.
Cosine,
Negative cosine. We're starting at the min, so it'd be negative cosine. The amplitude is still 1, because we're going from 2 to 3, so there's no. And then what is the period of this? The period is pi. So when we put pi into our pi in for theta, cosine is going to reach 2 pi, because the period of cosine is 2 pi, right? The period of cosine is 2 pi. So when we put theta equals pi in, we need to be putting 2 pi into cosine, because we got a full period of pi, right?
So
2 theta. This way, when we put pi in for theta, we get a full cycle because we're putting 2 pi in for cosine. So this is this graph, negative cosine 2 theta plus 2.
If we shrink the period, we need to do the opposite of the angles.
What's that?
So the period and the angle are inversely proportional?
Yeah, that's what happens kind of whenever when you affect the argument of a function, it kind of does the opposite of what you think, right? So if you're multiplying by 2, it makes the period shrink by 2. Okay, so suppose we were interested in finding, we want to know, all right, so this is starting kind of new stuff now. What if we wanted to find the coordinates of the rightmost point in the first quadrant? So I want the coordinates of the rightmost point in the first quadrant. Okay, so vertical tangent. So what would be true mathematically at a vertical tangent?
X is going to change like so little.
Okay. no change in x, right? For a change in what?
Change in y. T. Oh, theta.
Theta. So we want dx d theta to be what? 0. So at that point right there, dx d theta. So this whole thing with calculus and polar coordinates, it's like you're working in both systems, right? We're talking about as theta changes, we don't want x to change. So that's our d. For a small change in theta, we want the change in x to be 0. So notice you're working in both coordinate systems at the same time. dx d theta equals 0. But that's exactly what we want, okay? So how are we going to get dx d theta? Where's dx d theta going to come from?
Well, that, x in terms of theta?
Yeah, what is x in terms of theta? X equals? You know what it is. What is x in terms of theta? R cosine theta. And what is r?
The expression right there.
Exactly. Okay, so x equals r, which is negative cosine 2 theta plus 2 times cosine theta. So that's what x is for all the points on this graph. Since x is r cosine theta and r on every point in this graph is a negative cosine 2 theta plus 2, that's what we got. Okay, so what's dx d theta? Dx d theta is going to be, yeah, we could do product rule. So, do we want to, yeah, so derivative of the first would be
2 sine 2 theta.
2 sine 2 theta
Plus sine theta.
times the second plus
Plus negative.
so it'd be that was the derivative of first times second plus first times derivative of second. Let's do it that way. Derivative of second is
Sine negative sine theta.
negative sine theta. So that's dx d theta, and we will want the values of theta that are equal to 0. So this would be a complicated thing to solve. We would have to expand things, use identities, expand things. We won't take the time to do it. But you wouldn't be responsible for something that advanced. So let's. I just wanted to. Still, the principle and getting this set up is all fair game. So we will want the theta that makes this true, and the theta that makes that true would be the theta such that here at the dx d theta is 0 or the rightmost point in that first quadrant. So solve for theta.
And then if you wanted it in another quadrant, we just manipulate the sign.
Well, this will also give you, this is going to give us multiple answers, like, because it'll be cyclic, right? So this will give us all the answers. So it would give you all 4. Okay, so is there one that's... Okay, so what about, should we do...
We're probably going to have new physics contexts on exam 2, right?
Say it again?
There are going to be new contexts for the physics on the exam?
Potentially. Potentially, yeah. Okay, what about 4 or 6? Let's do one more. 4 or 6?
6.
6 has been requested. Is that consensus? Okay, so now we're going to go start at 0. And by the time we get to pi, we're out at 4. Right? So when we get to pi over 2, we're at 2. When we get to pi, you're at 4. And it's just going to, the raise is just going to increase for that whole pi. So on each, you just think, on each of these radial lines, you're getting farther and farther out from the pole till you reach 2, and then you get farther and farther out from the pole till you reach 4. So that it's going to look like that.
Is that Fibonacci?
I don't know.
No.
Maybe. And then back to 2 pi. So back to 2 pi, it's going to go from 4 to 0, just the way it came. So when you get to 3 pi over 2, you'll be at 2, positive 2. So it's just going to come in like this. Okay, what is this graph? This is y equals sine or cosine?
Cosine.
Negative cosine again, right? So, and this one has center line at 2, but has an amplitude of 2. So it's going to be negative 2 cosine theta plus 2. So negative 2 flips it over, times 2 makes the amplitude 2, and then the center line is moved up to y equals 2. Okay, so what about we want the highest most point? So we want to get the highest most point here. That's right. So now your highest most point will be where dy d theta is 0, right? For a change in theta, you don't want any change in y. So maybe this will be easy enough for us to solve. Okay, so dy d theta equals 0. So what is y? Y equals our sine theta, which in this case is negative 2 cosine theta plus 2 times sine theta. Okay, so dy d theta is 2 sine theta times sine theta plus negative 2 cosine theta plus 2 plus cosine theta, or times cosine theta. Did I do that product rule right? Okay, so
So I have a question.
yeah, sure.
So the y equals r sine theta. So that also equals negative 2 cosine theta plus 2 times sine theta.
For this problem, this is always true, right? In polar coordinates, that's always true. But now in our graph, what does r equal?
So r equals.
So I shouldn't have written y here. This is wrong. This is r. Sorry. So for this graph, r is negative 2 cosine theta plus 2, which we figured out by looking at the graph. So then for this graph, y is this. So dy d theta then is the product rule.
But that's also the name of the on the left in terms of. You could say y was negative 2 cosine x plus 2, couldn't you?
That would just be referring to the.
If you called this the y-axis.
Yeah.
If you called this y and this theta, that would be true. But this is r. I mean, this is, yeah. So whatever you called that. But it's r because we're going to graph it in polar coordinates. Okay, so what do we got? 2 sine squared minus 2 cosine squared plus 2 cosine. So sine squared plus cosine squared equals 1. Unfortunately, we have 2 sine squared minus 2 cosine squared. So that's not going to work. So we need this to be 0, right? So really, what we have is a quadratic function, but in these trig functions. So what we can do is we can solve for, we can get an all in terms of cosine. So how can we rewrite sine squared in terms of cosine? 1 minus cosine squared, okay? So we have 2 times 1 minus cosine squared minus 2 cosine squared plus 2 cosine. All right, let's get rid of 2's. So all the 2's can go since we're setting it equal to 0. Divide by 2. And then what we'll have is, it looks like we're going to have, then after we do that, we're going to have minus 2 cosine squared. And we're going to have plus 1 cosine. And plus 1. How do we do? So got rid of the 2's.
Yeah, checks out.
Is that check? Got rid of the 2's, and then I combined. I got minus 2 cosine squared. I got plus 1 cosine, and then plus 1. So we have a quadratic in cosine, right? We have a quadratic in cosine. So does it factor? Does that factor? So to check that, let's change the signs first. Let's do make that plus and minus and minus. So does that factor out?
I don't think so.
I do.
Yeah, I don't. That's good. That's really good.
So we got 2 cosine and cosine, and so we need a minus 1. So we're going to have minus 1 and plus 1, and when we add the middles, we want a minus. So I think it's minus and plus like this. Does that do it? 2 cosine squared minus cosine minus 1.
Nice.
So therefore, cosine could be negative a half, or cosine could be 1. Both make this work. And where does cosine theta equal 1?
That's 0.
Does that make sense for what we're doing? Does it make sense that theta equals 0? What's happening at theta equals 0?
Stop almost is where it returns.
Do we have a horizontal tangent? That's what we're talking about. dy theta equals 0. Is it horizontal there? Yeah, it works, right? It works. Theta equals 0. It looks like it's coming in. It's going to come in, and right when it gets to the pole, it's going to flatten out. And so that graph is telling us that. Okay? But we know that's not the one we want. The question was, what is at the high point in the second quadrant? So that's going to be this one. So this makes perfect sense, but it's not what we were asking. We were asking about this. So where is cosine theta equals negative a half? Theta equals 2 pi over 3. 120 degrees, or 2 pi over 3, right there. And so then how do we find r? You can find r then by plugging it in here. So this is our equation, gives us r for every theta. Did you catch all that? Does that make sense?
Why didn't we get like a root that gives us 5 pi over 3? Or 4 pi over 3? Isn't there one?
Oh, right, so we're solving this right here. Cosine theta equals negative a half. So there's, you get both, right?
Yeah,
So you get the second quadrant, but then cosine is negative a half there too. Yeah, so yes, you do get, that gives us both of them. So let's write that down. But back to my original question, I said I want the coordinates of that high point in the second quadrant. So you would only pick that. But this equation gives you both. Cosine theta negative pi over negative half gives you both the top and the bottom, because your x coordinate is negative a half. On the unit circle, not this thing, okay? Your x coordinate here looks like something greater than 1. But we're looking at the unit circle to get the theta that gives you a negative a half, right?
What other coordinate systems are there? Are there many, or is it just a handful?
Let's see.
Is the complex plane considered rectangular?
Yeah, the complex plane is rectangular. You got reals and imaginary, right? Real and imaginary. So that's still kind of, that's a different coordinate system, but it's based on rectangular coordinates. But these are the main two. So rectangular coordinates and polar coordinates are the main two. I'm sure there's like the hyperbolic plane, where it's only actually this half plane, and the further you get away from the x-axis, it's hard to explain. But like if you were walk 1 unit of distance down here, if it looked like if that was 1 unit here, that would be 1 unit would be like hit that up here. So it's like distance changes as you get further away from the x-axis. So if you're walking towards the x-axis, you'd never get there. You would just keep walking forever, and you'd never reach the x-axis.
The farther down you go, it bumps you up.
No, it doesn't bump you up. Your distances are getting compressed. They're shrinking.
That's cool.
Yeah, I took a whole course on it. It's really cool.
What's that called?
What's that? It's called the hyperbolic plane. Okay, so let's just in general go back and draw this thing again. There's a 2, 0, 2, and 4. Oh, it was so much better before, but I'm gonna try it one more time. There we go. Reach. There we go. Better. It's really good, right? You're laughing because it's so good, right? Okay, so what if we wanted to know, say here at pi over 2, what is the slope of the tangent to the curve at pi over 2? What if we want to know that? What would that be a matter of mathematically? What would we want to know there?
Would that be d y would be x?
He wants dy dx. Agree with that?
We keep the equation of the tangent line, don't we?
Well, that would require the slope. I'm asking for the slope first. So the equation of the tangent line would require the slope. I'm asking for the slope. So what mathematically is the slope of that? He said dy dx. Agree with that? Yeah, slope is dy dx.
Yeah.
Slope is dy dx. Okay, how are we going to get dy dx?
Is it r sine theta over r cosine theta? Take a derivative of that?
Theta is dy theta divided by dx.
Yeah, so this is the same as what we did with parametric, right? And what do we do when we do dy d theta? We just saw it. We have to do the product rule, right? Because y is r sine theta, and x is r cosine theta. So what's dy d theta? So, but now r is whatever your function of theta is, right? R is a function of theta. For whatever graph you have. In our case, r as a function of theta was 2 minus 2 cosine theta.
Yeah.
But now we're just talking generically, right? So r could be any function of theta that we have, and we want dy dx. So what's dy d theta? Well, it's going to be r prime theta, or dr d theta. Let's do it that way. Dr d theta times sine theta plus r times what? R times cosine theta.
Plus x.
Y plus x. We're doing the product rule on r times sine theta.
We can't just say that that's x r cosine theta.
Yeah, I suppose we could. But but all this stuff is going to be in theta, right? All this is going to be in theta. Dr d theta will be a function of theta. That's a function of theta, so we want to leave it all in terms of theta. And then what's dx d theta? dx d theta is going to be dr d theta times negative sine theta plus r times, whoops, I did both. That should be cosine. Derivative of the first times the second, not times the derivative of the second. Derivative of the first times the second plus the first times derivative of the second. Okay, so for this one, what is dr d theta? Dr d theta is 2 sine theta?
2 sine
And r is 2 minus 2 cosine theta. So let's do the whole thing. We're going to have 2 sine theta, actually squared, right? That's 2 sine theta times another sine theta, plus 2 minus 2 cosine theta times cosine theta over 2 sine theta cosine theta minus r sine theta. So what is this? This is a slope function for this whole graph. Given a theta, what does this give you? It gives you dy dx. So it gives you, for
What
any,
makes sense of that?
what's that?
This is a derivative
Dy
with
dx.
respect to x, but it's in
Sure.
a
It's a
third
function of
derivative.
theta. It means you plug in a theta, and the value that you get from this ratio is dy dx. It's the slope in Cartesian coordinates of the polar curve.
Okay.
Makes perfect sense. Okay, and I said we want to know the slope at pi over 2. So this is going to be easy, because what's the sine of pi over 2? Sine of pi over 2 on the unit circle.
0.
It's one of those two.
1.
1. Sine of pi over 2 is 1. Cosine of pi over 2 is
0.
0. So it's going to be, everything's going to be easy, right? So this is sine of pi over 2 is 1, so we're going to have 2 plus 2 minus 0 times 0 over. All right, before we finish it, prediction for dy dx. Predict.
-1.
Positive or negative? Negative. Looks like negative 1-ish, right? Negative 1-ish. All right, what will this be? 2 sine. Oh, I forgot to write this in here. This is our 2 minus 2 cosine theta here.
2 sines, 2 sines squared.
That's r, right? I just wrote r again. So this will be 0 minus 2 minus 0 times 1. Did I get it right? And what do we get?
-1.
Negative 1. Which is what it looked like when we guessed. Slope of that line at theta equals pi over 2. So then you could write the equation of the tangent line now. You've got a point.
Okay.
What Cartesian point is that? 0, 2. X equals 0, y equals 2. You got the slope. Easy. Write the equation of the line. Okay, so this is,
You couldn't express a line in polar coordinates, could you?
yeah, you did for your homework. Definitely. So what line is this then? It's y equals negative x plus 2. Right? So let's do it. I'll do it in blue. R sine theta equals negative r cosine theta plus 2. So then you have r sine theta plus r cosine theta equals 2. Factor out r. Sine theta plus cosine theta equals 2. So r equals 2 over sine theta plus cosine theta. That's the equation of that line.
Okay, so sine equation, you're going to give some number. So then it's just 2 over that.
2 over sine theta plus cosine theta. I'm using S and C just as abbreviations for sine and cosine. So this line in polar coordinates is 2 over sine theta plus cosine theta.
So for any theta as you rotate around, it's going to give you some point.
So plug 5 and 2 into that. And arc it.
Yeah, so you're going to rotate with thetas, and whatever your theta is, the distance from the pole will be according to this expression of theta. And that will give you the points on this straight line in the polar plane.
But then how do we get infinitely many points? Or is it a line segment?
No, this is a good question because sine plus cosine is going to be some cyclic thing like this, right?
So the limit as
Because I want every point on the line. And I don't know how to do
Right,
that.
so, okay, so when this goes to 0, when this gets close to 0, this thing is going to get close to infinity. So what's going to happen is at some angle here, there's some angle that makes this 0. And so we have to get really, just this people limit, we get really, really close, and we're just going to get every point.
And it'll spit out 1 million points as it expands.
Zillion, yeah.
That's insane.
Yeah. So as that sum goes to 0 for some certain theta, imagine theta just getting very, very close to that, and we'll get every r value up to infinity as we get closer and closer to that angle.
Wow.
The angle, well, actually, the angle is going to be 3 pi over 4, right? 3 pi over 4 is going to be the angle. So as we get angles closer and closer to 3 pi over 4, we get every point.
And then what happens when we go past it?
Well, it's undefined, and then as soon as we tip past it, now we're going to get all these points down
It
here.
was on the other side.
Yeah. That is cool. All right, so we got to talk about areas in polar coordinates. So before we do that, we want to think about what is the length of the curve on a circle. What's the arc length of a circle? So if we got something like this, and you take some angle, call the angle alpha, and the circle has radius r. What is that length right there? We usually call it S. So arc length S equals what? Alpha over R? Alpha times 2 pi R? So if alpha is what? Alpha is, by definition, is the number of radius lengths that the angle, number of radius lengths of arc length
Wait, what?
that the angle cuts off. Okay, review of angle measure. Okay, so what does that mean in radians? It means how many radius lengths we cut off by the angle on the. So the number of radius lengths that angle cuts off on the circle. So then if we want how many units that is, what actual distance that is, if our radius is r, and that's alpha is how many radius lengths that is, then what is the length of that arc?
It's going to be r over 2 pi times 2.
Yes.
But times 2 pi, right?
What is a radian?
What's that? That's what I'm explaining to you. A radian is the number of radius lengths that this angle cuts off on the arc length.
Or divided by 6.
How long is it? 180? divided by the.
Okay, so it's r times alpha.
Pi d over.
You're joking, right? Okay, so it's going to be
Alpha.
r times alpha. Okay? Because alpha is how many radius lengths, and the r is the length of one radius. So to get the total length of the arc, you're going to take the length of one radius times how many radii you have. Because that's what alpha is. It's how many radii you have. So for instance, that looks like maybe 1/2 of a radius, right? That looks like 1/2 of a radius. So 1/2 of a radius is that distance. Do you see? Okay, so that's what arc length is. Radius times angle gives you arc length.
This is just for circles.
That's right.
So what is a radian?
A radian is the number of radius lengths
Okay.
of arc length that the angle cuts off. That's what a radian is. That's what we're measuring alpha in. So like for this one, it's about 1/2 of a radian, it looks like. Pretty close to half a radian. Why? Because that is like 1/2 of a radius length.
So arc length is radius times angle.
That's right. Okay, so if we have some polar curve here, r is a function of theta, and we want to look at, say, the area, some starting angle, some starting angle and some finishing angle, and we want the area in here. Okay, so the area in there, how are we gonna, we've got this variable radius, or variable, distance from the pole here. R is a function of theta. So what's gonna be our general strategy to calculate this area? Has anyone learned anything this semester?
We'll have to integrate little bits of
Integrate what?
little bits of area.
Little bits of area. And what will a little bit of area look like?
Would it be easy to go from like the origin to the curve?
Okay, so what will the shape be?
Just a line. With a little
Delta R times the
typical
angle.
strip that goes, yeah.
Typical strip will be like,
It's pizzas.
it would be like a slice, like a triangular slice will be the typical strip. So imagine, what?
Why are we choosing such a strip?
Because we're thinking about angle, the angle changing from theta 1 to theta 2. So a little change in theta will give us like a wedge-shaped typical strip, right? And so here's where we want to find the area of that thing.
Why does this work for this non-circle R?
We're going to do a typical strip.
Oh, so the point could be on some magical circle.
And we have a function, r is a function of theta. It doesn't have to be a circle.
So theta sticks out R.
So we're just relating the distance to the radius.
Yes, that's right. So this distance, this is our r. So imagine this is a very, so what is this? This is a very small, this is our delta theta.
So that could be part of the circle.
This can be any function. R can be any function of theta. Like the ones, all these trigonometric functions we've been doing. 2 plus 2 cosine theta, that's why I'm drawing it just randomly. Okay. But what we need is, we need this area of this typical,
So R alpha applies for any polar curve. To get the R length.
no, it only applies to a circle, but we're making a really small strip. So actually, we're gonna do a triangle. Okay, so we're gonna do like we're gonna do the area of a triangle. So what's the area of a triangle? 1/2 base times height. Okay.
And is that because the change in data is so small that it's basically a line?
Yeah. So it's basically a line, but then we're gonna use the arc length to get that line, because when it gets small enough, then they're virtually the same. A little bit arc length, yeah. So what is our base? Our base is not delta theta. It's like the arc length, right? So the base is r delta theta. That's from this, right? It's the angle, the amount of angle times the radius. Depends on how far out you are. So that's our base. And then times the height. What's the height? R. One half r squared delta theta. So that's our typical sliver of area. Right? So the base is this little distance right here, which we're going to use the arc length formula from circle. And that's going to be like the base of our triangle. And so that's going to be the angle times the radius. Angle delta theta times the radius. And then the height of the triangle is actually that whole distance r. So we get 1/2 r squared delta theta. And what are we going to do? Add them all up.
Just from the starting angle to the ending.
Right, we're going to integrate from theta 1 to theta 2. All our typical triangular wedges, starting at theta 1 to theta 2. And that's going to give us that total area between theta 1 and theta 2 out to our function, the blue function.
It still seems like you're taking a super zoomed in circular snapshot, because then what happens when the curve starts bending inward? Like when it's concave up? Like that's not the arc that we're looking for. So I feel like it's treating a point as if it were along some circle.
Well, so when you have the triangles that are like quote unquote bigger, like the one I'm showing you, we're just approximating, right? We're getting an approximation for the area when we add it up. Okay? But so then it's when delta theta gets super, 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 super small, then your approximations get better and better and better, just like we've always seen before. Okay? Because you're
No, I feel that, but we're approximating according to a rule. And the rule is, I feel like we're treating each small section as some arc on a circle.
right. That's we're using right. So we're using that. We're taking that distance and making it a line segment. So we're taking that distance r delta theta, and we're saying, okay, we're going to slap that on as a line segment. And so when delta theta gets very, very small, very, very, very small, then that does the job. What's that?
You're going to approximate the arc segment. By the
No, because when delta theta gets very, very small, we basically have a zillion little straight lines in the end. Right? When delta theta is very, very small on a curve, you've got a little itty-bitty line segment, essentially.
Yeah.
Right?
So,
You zoom in far enough, it won't be curved anymore. Everywhere.
so like if it's like curved in, not curved in, but like there's like a dent, like and you're taking small strips, and you eventually get to that the point. So like
Talking about a corner point?
corner point.
Well, that's not differentiable, right? So if it's not differentiable there, then you'd have to kind of start over. Like you'd have to do it to that point, and then integrate to that point, and then start again, integrate beyond that.
Okay.
This is for, if you don't have any sharp points. Yeah.
So for this, it's like when you get really small delta thetas, and the points are not the point. The graph is like kind of curved inwards.
Okay.
What about when it's curved outwards? Because this seems like it's almost parabolic, so you can take like two different points and be straight. But that seems like you get an angle and you kind of like a weird triangle.
Yeah, but you got to think the delta theta keeps getting smaller and smaller and smaller and smaller and smaller. So even if it's heading in towards the origin, heading away from the origin, when theta gets small enough, that amount of error keeps shrinking. So So the little segments that are parallel to the direction you're going, even though this may not be parallel, they're small enough that it eventually fits the curve. You got to think of it getting really, really, really small. It's getting super, super small.
But that works there because the distance is.
I mean, it's the same thing as when you do rectangular coordinates. It's the exact same thing. What about when the curve is, going up really rapidly, and you're using the tops of your rectangles are straight like this? It's the same thing. You see? So it's going up really, really rapidly, but you're using a straight line this way.
Okay.
That's the same thing that's happening here. When they get really, really, really small, then so here's your error right there, that triangle. Well, when they get really small, that error goes to 0.
Okay.
It's the same thing. Okay, so let's go back to one of those that we were working on. So let's just do this one. Back to this one again. And so suppose we want to find the area of this part right here. What's that amount of area?
The integral from
Integral from?
theta equals 0 to pi over 2.
Yep. Of? And what was this was r equals 2 minus 2 cosine theta? Okay.
Of 1/2 times 2 minus 2 cosine theta squared.
Are you going to want us to evaluate these?
Yeah, if we want to get the area, we got to evaluate it.
Oh, man.
So, yeah.
This is like synthesizing everything we've done.
Yeah, so this brings in, so we did the trig integrals, right? We did trig integrals, so we want to multiply that out. I mean, we won't do it now, but we'll just multiply it out and talk about how you would do it by hand. So it'd be 4 minus 8 cos theta plus 4 cos squared, right? Easy, easy. How do we do cosine squared?
Half angle.
Half and not 1 minus sine squared, because you're back where you started, right? If you want minus sine squared, it's the same thing, basically. So half angle, right?
I think this is not bad.
That's not bad. It would take 5 minutes, but we won't do it. But if we were to evaluate that integral, let's put it in the graph right here. That integral would give us that area.
And it would make sense, like, because it's squared units, so it'd be Cartesian. Right? Like we'd be able to approximate, like, it looks like something like maybe 2.
Right, so yeah, if we were to approximate this, that's good. So here is, this rectangle has an area of 2, right? It's 1 by 2.
Maybe 1.
So what would you guess? Something greater than 1, 1.5-ish? Okay, let's do it.
Yeah, let's put that in.
So what do we say here? See what I did there? That was pretty slick. All right. 0 to pi over 2. And we want 1/2 2 minus 2 cosine x dx squared. Do I have it right? 1/2 2 minus 2 cosine squared. Should be more than that. Seems like it should be more than 0.7, right? Unless when I drew it, so it probably let's actually
Oh, Oh,
graph
yeah.
it, because when I drew it, I may have gone out too far, right? So the actual thing may stay a lot closer to the x-axis when you do it. So let's just get a picture of it. So the function is 2 minus 2 cosine theta. I want to graph that. Zoom out. So I'll draw my block again, or let's draw 1 unit. So half by 2 is 1 unit of area, right? So does that look like about 0.7 of that?
Sure.
Yeah.
Okay.
So yeah, I just drew mine was too far out, so it stays closer to the y-axis. So this rectangle has an area of 1 unit, and we got from ours we got 0.712. So yeah, about 3/4 of that.
So is it always expectations rate triangular strips?
Yeah, this is a 1/2 r squared d theta. You're always going to use that.
Okay.
Yeah, because that's how polar coordinates work. You're going to sweep theta this way, and r is going to be distance from the pole. So as you sweep theta, a typical element is going to be the wedge, the triangle. Yeah. Always.
And that will account for loops and repeats.
Yeah, that's why I drew the very generic. You know, when I drew when I drew it, I drew just a generic, any r is a function of theta,
Sure.
right?
So what happens if we've got some loop coming out over here and one number over here? Is that going to give us twice the area, or?
It depends on the angle, right? So yeah, so that's a good question. So do we have one of those? Gives us loops.
Or like the butterfly, what would happen there?
For that.
Number 4?
Yeah.
All right, so let's sketch number 4 and do an area problem for that. So I'll do this fast. So we're starting at 1, and then pi over 2, we're at 3.
Get back to 1.
And then back to 1.
Yeah.
And then, so what happens as we go from pi to 3 pi over 2, somewhere in the middle, it reaches r equals 0. So you're at the pole, and then r is negative till 3 pi over 2, negative 1. So here's 3 pi over 2. Where's negative 1 for 3 pi over 2? Here. So somewhere, as we go from pi to 3 pi over 2, we're going to go through the pole, and then it's going to turn negative and go out to negative 1. And then it's going to come back. So if I do the integral from 0 to pi over 2, it knows nothing about this because the angles, this angle is right here is like somewhere close to 3 pi over 2.
It's outside the bound.
This is a negative r for some angle that's way outside the bounds. So if we do the integral from 0 to pi over 2
Is it going to give you all
of 1/2 r squared d theta, all it's going to be looking at is this right here. It's going to give you all that area right there.
inclusive of that little tiny piece?
It's not even, this is gone. It's not even in the picture. So it's just going to be from like this. That's the area you're going to get.
No way.
Starting from there to there, inside all there. That's the area you'll get.
So then you would have to subtract the area from that little piece then if you wanted to find like an exact everything. Does that make sense?
What are you saying now?
If you wanted to just find that area, that like donut piece, you have to take out the center for that region. Like you'd have to subtract a different integral, a second integral.
Okay, I think I know what you're saying. Let's see here. Okay, so now you want what? All this area like this?
No.
Yeah, sure. Same question.
Okay, I think if you
Or if you just did 2 pi, it would automatically subtract.
Yeah, what happens if you put the balances to
one
period?
question at a time, y'all.
Sorry.
So kind of the more interesting question is, what's the area inside the loop? How about that?
That would just be from.
So that's really a question you'll see. So we want the area of one petal or one loop, okay? Because some of these, did you get to draw any that were like flower, like you get a bunch of petals? We never saw one of these. Okay. Anyway, so some of these turn out you get multiple petals. So this is like, so what is the area inside there?
So we would just have to find the theta where it starts and then where it starts.
Okay.
and ends.
So what is my theta 1 and my theta 2? What's true about those two thetas?
They pop out the same R.
Which is what?
0.
Right. So the starting theta is where r equals 0. And the ending theta is where r equals 0. All right, so what is the equation of this? This is going to be sine plus 1. So we're going to do plus 1. The center lies at 1. And it's going to be 2 times sine because our amplitude is 2. So what is the period?
Looks like it's still 2 pi.
Oh, it is 2 pi. Good. Yeah, few. All right, so is this 2 sine plus 1?
Yeah.
So what? We need that to equal, we want to know where that equals 0. So we're saying sine theta is
Where sine equals -1/2.
-1/2. And there's 2 places. And that's when we know in third and fourth quadrant. It's going to be at 7 pi over 6 and 11 pi over 6. So that's going to be our theta 1.
Wow.
And that's going to be our theta 2.
That's cool.
And so to get that area of that loop inside there, it's going to be the integral from 7 pi over 6 to 11 pi over 6, 1/2, 2 sine theta plus 1 squared.
That's it. Wow.
So if you were to make your.
So that would give us that area inside. You don't have to worry about it being negative because r gets squared, right?
Right.
R gets squared, so there's no negative areas in these. They're all positive. So if you wanted, you'd have to, so you're going to go from 0 to 2 pi, and then you're going to subtract that if you wanted that thing you were talking
It
about.
wouldn't subtract the automatic, like on its
No,
own.
because it's,
Because the radius is base squared, so.
r is getting squared, right? So your d is based on r squared. So you would just keep, so
So in doing 2 pi would
there's
have.
no negative contributions in these areas because r squared.
So then if you did from 0 to 2 pi, it would give you the entire inner circle and then the extra smaller petal, right? That's what the sum would do, that's what the area would give you.
Yeah, it would be more area than what's in the outer perimeter.
Okay.
It'd be everything inside the outer perimeter plus an additional one of those.
Right.
Oh,
Yeah. So if you want the donut that we were originally talking about, you have to do the integral from 0 to 2 pi and subtract this.
Okay. That takes a long time, actually.
sounds like a great example.
Pretty good question. Oh man.
Wow.
But this is just the little leaf, the little petal inside.
Right.
Other questions? Okay, so study. So, like I said, this 6-page review sheet plus the additional documents that I'll post today will be comprehensive review. Don't study topics that we did outside of that because it won't have everything that we did. But those two things together will give you everything. No, everyone gets 100 on the one. Everyone's 20 on the
You in the bundle?
Hey, nice try. That's a good try.
Okay, so can we shoot to start tomorrow at 10? We'll start the exam at 10 tomorrow. And I'll be in my office at 8:30. 8:30.
That's weird. Do you remember that in class thing? In class, I think worksheet or sheet that we
Yeah.
did. I was for a job interview.
Okay.
Do you want me to do it now or shall I do it tomorrow at 8:30?
You never